All right, hey everyone. So it looks like we don't have that many people joining the Zoom, and that's okay. But in case you missed the meeting and wanted to watch the lecture back, I'll be recording it anyways. So I guess I'll start. 1 minute. All right. So today we're going to be going over the life cycle of a star. I'm just changing some things. Anyways, today is day 4. We're all over halfway done with the course, but I'm going to be going over the life cycle of a star. So if people are on the Zoom, I would say, put an emoji in the chat as always to see how your life is going. All right, so today we're going to cover the stars in the universe, specifically what stars look like, what they do in the universe, how we see them and evaluate them. Also, how stars form, which is really cool and really important part of astronomy. Stars, like how specifically they function. Also, their composition, like what elements they're forming, which is a really cool thing that they do. Also, the types of stars, how we classify them by like size and temperature and all that. And finally, we're getting into the end states of the stars, like you might have heard of supernovas or black holes, all that kind of cool stuff. So let's get going. So our first little road is the stars in the universe. Okay, I guess we might as well start with the definition of star. Of course, you've seen them in the sky, but specifically, a star, I would say, is a luminous object. So that means something that glows in space that is made out of matter that is in a plasma state. So that means that it's really hot and there's a lot of pressure on it. And there's all sorts of like chemical things that happen when something is in a plasma state, but for our purposes, it means it's really, really put under a lot of pressure and it's really, really hot. So, anyways, a star holds itself together by its own gravity, and it also undergoes nuclear fusion, which produces energy and allows it to glow. But we'll get into that in a minute. Anyways, so in terms of like numbers and statistics and all that, there are 200 billion trillion stars in the universe, which is a crazy amount. So astronomers have calculated this number by taking the average stars in a galaxy, which is around 100 million, and multiplying it by the number of galaxies in the universe, or that are believed to be in the universe, which is 2 trillion, which is, I don't even know how to like say this. I've heard that if you think of like billions and trillions in terms of seconds, um, I think, okay, wait, I don't remember what the exact thing is, but a million seconds is something around like 2 days. And a billion seconds is like, I think something crazy like 39 years. So if you were to multiply that by 1,000 again, like a trillion seconds would be like tens of thousands of years, which is crazy. So that's basically just a demonstration to say that when you multiply numbers by like thousands, like billions, trillions, millions, it just gets to numbers that are so large we can't even compute them. So all of that is to say there are a lot of stars in the universe. Um, but that being said, something that's kind of crazy is that stars and gas and other matter only makes up about 4% of the universe. I'll be getting into the really cool stuff later, like dark matter and all that. But matter as we think of it, the universe is so large that stars and that kind of thing only makes up about 4% of the universe. Um, Anyways, in the Milky Way, which is our galaxy, there are 100 to 400 billion stars, and that's a lot. But the stars are like really far apart in the universe. They tend to be about 5 light years apart, which means that in like if you were traveling at the speed of light, which is the fastest speed we know of, it would still take you 5 years on average to travel from star to star. So like when you think of that in terms of humans actually traveling to other stars, it would take, if we could get to the speed of light, which is very hard, but if we could, it would still take years and years to reach other stars. But it's possible. Don't want to say it's impossible, but things are very far apart in the universe and even in our own galaxy. So we're going to be talking specifically about like luminosity and brightness, and these two things are different. So, okay, so a star, like I was saying earlier, it undergoes nuclear fusion and it exerts energy. This energy is specifically in the form of light. So we know that stars exert a certain amount of light based on how big they are and how much like fusion they're doing. I'll talk about that in a minute, but we know based on a star's size and like temperature and all that how much light it should be emitting. But as light travels through the universe, it spreads out and it gets dimmer. It like gets a lot weaker. So from that, by the time light hits us, it appears a lot less bright. So we because we are located on Earth and like our perspective is from that of Earth, we classify how bright a light appears in apparent magnitude and brightness. So if you talk about like naked eye observation, which is what people have done for thousands of years, they classified 1 as the brightest kind of stars and 6 as the dimmest. And as we started getting telescopes and like really fancy equipment and all that, people started making even more classifications. So like they got into the negative numbers as things are really, really bright. If you look up here, I'm gonna get my clicky. Where is it? Okay, as we get up here, something like the sun, which is the brightest object nearest like to us, it's a brightness of -25, and then things over here, this is like the standard thing. Sirius is about a 1. Naked eye limit is like the least bright thing you can see, about a 6. They're kind of arbitrary numbers, but it's just like a scale that we put things on based on how bright they appear. But anyways, using this apparent brightness, scientists use the color that the star like appears to us, paired with how bright it is, to determine how far away it is from Earth. A second ago, I was saying that stars exert a set amount of light based on their size. So we know how bright, like how much luminosity that star should be putting out into the universe, but based on how it appears to us, we can determine how far away it is based on like how much that light dims by the time it gets to us. So that's an important tool that we can use when determining how far away stars are from us. Anyway, a thing that I'll be talking about in a minute that is pretty important is that temperature correlates with luminosity and also with color. So you can see how, I'll talk about this in a minute, but it's really important. But things that are hotter, you can see the numbers are getting up here. Temperature in Kelvin measure, it's like Celsius, but scientific basically. But as things are hotter, they actually appear bluer, which might seem a little counterintuitive, but that's something that occurs. And as things are cooler, they actually start appearing redder. But anyway, if you look at how bright something is appearing and also the color, which is related to the temperature, you can, there's a thing called a main sequence, and you can see like, you can figure out like the distance, but also the mass and the age of the star. I'll be talking about that in a minute. But temperature is related to color, and you can like compare color with brightness to figure things out. Anyway, so nebulae or nebulas, whatever you want to say, are often referred to as stellar nurseries, and that's because they are the places where stars tend to form. So they're often, or they're always, okay, so wait, no, I should first say that they are like clouds of gas and particles and like molecules and all that that are just like floating around in space and aren't like bound to anything. That's what nebulae are. And yeah, they're the result of exploding stars and that kind of thing. And they are dozens, anywhere from like a few to dozens to hundreds of light years in size, which is very, very large. I was saying a minute ago, like stars tend to be about 5 light years apart. So nebulae are like the size of like distances between hundreds of stars. They are very big. Their makeup depends on the kind of star that formed them. So stars have specific elements inside of them. So then when they explode, they release those elements all across like their surrounding area. And then that is what we call a nebula. And then that cloud of gas is determined by like the star or anything else that ended up forming it. So atoms other than hydrogen are formed inside of stars. So any other atoms that are like floating around in the clouds of gas, we know that they were like formed from stars. They also emit all kinds of light. So you can apply like different filters from like UV to infrared to like also visible light to view nebulas, a lot of the pictures you see of them aren't actually in the visible light spectrum. They normally look like little, just like gray and brown clouds when you look at them with visible light, but if you like apply pretty filters to them, they look all sorts of colors. And those are typically the kinds of pictures you see, like this one. Anyways, so, oh yeah, here are more really, really pretty pictures. This one is called The Pillars of Creation. It's like a really famous picture, all of them. Anyways, here's the closest nebula to us. It's 700 light years away, which is very far, but it's still in our galaxy. Our galaxy is like tens to hundreds of thousands of light years across. But anyways, Helix Nebula. So it's pretty cool. This is part 2, the formation of stars. But first, I'm gonna check to see if anyone is in the waiting room. Oh my gosh, there's someone in the waiting room. Okay. Okay, wait. Hi. You're here. Okay, wait 1 minute. Yes, I guess we are the only ones here, but I really appreciate you being here. Thank you. Anyways, I hope you like caught up with all that. But anyways, I'm gonna get into the formation of stars. So this part is pretty complicated, but I'm gonna try and explain it the best I can. So a minute ago, I was talking about nebulae or nebulas. As being the stellar nurseries, so the place where stars form, because they're giant clouds of gas, right? So then we go onto this. Stars come from those nebulae or gas clouds, which you can also call like molecular clouds because they have all sorts of atoms and molecules in them. So this gas kind of bounces all around. And at first it's just kind of like randomly bouncing around because when gas is like when particles are in a state of gas, they kind of just bounce around everywhere because they have a lot of energy. But eventually, all this bouncing around ends up forming patches of or clumps where the particles are more like there are more of them in one area than there are in other areas. So it's gathering in certain spots all around, and it's not really orderly. Like I said, it's just random. But when things clump up in certain spots, they start like these particles start to like, gravitationally interact. So you know that gravity in our context pulls things towards the ground. So have a pencil, whoa, you drop it. That's what happens on Earth specifically. This might be a little bit of a high concept, but I'm going to try and explain it. But gravity isn't just caused by planets. Gravity is something that all objects can exert on other objects. The only difference is, or like the only factor that determines what happens is the size of the objects that are interacting. So for us, the Earth is the largest object anywhere near us. So anything that you drop or anything that you just like let be in free air is going to fall to the ground because the force of gravity that the Earth exerts around it is the strongest force like in the area. So if you were in like completely empty space with no large objects around you, and I have like 2 little rocks over here. So if you had like 2 rocks that were like relatively the same size and you just kind of let them float through space, it wouldn't be that one would travel to the other or that one would travel to the other. They would like attract each other and go towards each other at like roughly the same rate because they're the same size. So when you have the Earth and you apply that, this falls towards the Earth because the Earth is so much bigger than this one little rock. And this rock actually does pull up on the Earth, but the Earth is so big that it would take a lot more energy than the pull of this rock to like pull it upward. I hope that makes sense. But yeah, basically what you need to take away from that is that larger objects have more gravitational force and they can pull other things into them easier, like the larger they are. So when you apply that to like gas particles floating around in space, this means that when certain gas particles kind of fly around and they end up clumping up together in one certain spot, that clump is going to be the largest thing in the like area near it. So it's going to be the thing with the strongest gravitational force. So then other single particles that are kind of floating around are going to be pulled in towards that clump. And then that clump in turn is going to get bigger because it pulled in a bunch of other particles. And then because the clump is bigger, it's going to have a stronger gravitational force. And this is kind of like a cycle. You can think of it like a cycle. But basically, the bigger something is, the stronger gravitational force it has, the more stuff it can pull in, the bigger it gets, etc. So I said that right here, but like gravity begins to interact with the particles and pull the particles together. And as the particles are pulled together, they become like bigger clumps, and the gravitational force from that increases. So then from there, you have this giant, like I said a second ago, it's like a really big gas cloud, but there's like also a kind of big, getting even bigger by the minute, gas cloud in the center that has like a bunch of gravitational force. So it's going to start pulling all the particles all around it in towards it, and they're going to start going into orbit around it, as you can see here. So for various reasons I'm not really going to talk about, all the particles like near that one little thing in the center are going to start orbiting around it in a disk shape, kind of. As you can see right here, you have your little clump of particles that we actually call a protostar in the center, and all the gas orbiting around it, what you call down here a protoplanetary disk. My pointer? Protoplanetary disk. I don't know if I explained that very well, but basically, all the particles are forming a protostar and a protoplanetary disk because of gravity that's just like attracting particles. So anyway, the more gravity something has, or like the more gravity, or the larger the ball of particles is, the more gravity it's going to exert on things around it, but it's also going to exert more gravity on itself. So what this means is that it's pulling the particles of itself in, like more the larger it is. So this increases pressure in the center of the star. So something, once the like little clump gets turned into a really, really, really big ball, it's exerting a lot of pressure on the inside of it. And because of the pressure, there's also like a lot of heat. And because of the heat and pressure combined, I said this at the beginning of the lesson, but a star is a luminous object that's in a state of like plasma. So, because of all the pressure and the temperature, the particles of dust or stuff in the center of the star turn into a state of plasma, and this begins nuclear fusion. Talk about nuclear fusion later. But basically, nuclear fusion is when things are in a state of plasma, which means that the atoms are kind of separated into their little parts, and then they push together and they form new atoms. And well, not new atoms, but they like rearrange the parts of the old atoms to make different atoms. And this process releases a lot of energy. It creates new atoms, and it releases, like I said, energy and light. And this exerts an outward pressure on the rest of the star from the core. So that means that the core is exerting an outward pressure, and the entire star is exerting an inward pressure because of gravity. And eventually, the star reaches a kind of equilibrium where the outward pressure is equal to the inward pressure. And this like state is when the star doesn't really take in any more matter because it has like outward pressure on it. So during this state, the mass is determined. So pressure from, like I said a second ago, gravity reaches equilibrium with pressure from fusion. And at this point, the star's size and specifically its mass is determined, which is really important, and I'll talk about that in a minute. But anyways, like I was saying a second ago, any remaining gas that wasn't taken into the star orbits the star, or it would be a protostar at this point, but orbits the protostar, and it ends up flattening and forming a protoplanetary disk. And what's really cool is that from this disk that is still a bunch of just gas and other particles, this is what forms planets. So we have a more concise diagram. So you can see here, this is a giant gas cloud and cloud of dust that's in outer space. It's from, other previously exploded stars. Eventually, clumps start forming within the cloud, and those clumps end up exerting a gravitational force around them that pulls more clumps in towards them. So the clump ends up getting larger and larger. And on this diagram specifically, it says that it's denser and denser. So it's like pulling in all the gas from around it. And eventually the remaining gas ends up orbiting it in a disk shape. And the core ends up having a lot of pressure and heat in the center of it, which ignites nuclear fusion, and eventually the pressure on the inside, like pointing in, is equal to the pressure pointing out, and it stops taking in any more matter. But this gas is still like orbiting, and a similar thing happens with the gas orbiting it as with like what happens to the actual star. Basically, just like little particles end up forming clumps that attract more particles into them, and eventually they also turn into spheres, and those spheres end up orbiting the sun, which is cool. And that is how a solar system forms. Of course, planets don't always form around a star, but in the case where planets do form, that's how they form, from this little disk, this orbiting disk thingy. So from there, a star is born. Anyways, so from the birth of the star, there are some things that are determined. So like I was saying a second ago, for whatever reason, stars, like each individual star ends up having its own like set mass where it's in equilibrium. The force going in is equal to the force going out, and that's like the set mass that it's going to have. So from there, the size of the star is determined. So basically, the star is going to be like, it's going to have an amount of mass, and the more mass it has, the more gravity it has. So if a star has like a lot of gravity, it's going to pull itself in more. And so that means that like sometimes stars that have more mass are actually smaller because they have a higher gravitational force. This gravitational force is also going to impact like the temperature, and like the gravitational force is because of the size. So the size, or like more accurately, the mass is really important. So bigger stars that are more massive produce more energy because they have more gravitational energy. So in the core, there is more energy happening, which means that they're hotter. And weirdly enough, we wouldn't really think of this, but in astronomy, things that are hotter are actually bluer, and they're brighter because they are producing more energy. And if you think about like the electromagnetic spectrum, I tried to explain that last week. It's a little bit complicated, but basically, light waves with more energy tend to appear more purple or blue, as opposed to things with lower energy that appear more red. So anyways, yeah, in the case of astronomy, things that are bigger produce more energy, and so they're hotter and bluer and brighter, and things that are smaller, like stars that are smaller, produce less energy because of gravity, and so they are colder or cooler. They're not cold, they're still really, really hot, but they are cooler, and they're also like more red, and they're a little bit dimmer. So because and okay, so stars' mass also determines its lifespan. So stars with more mass have more gravitational energy. So all the energy in the core of the star, it's like going to be higher. So it's actually going to be burning through that energy faster, or burning through its fuel. And we think of its fuel as hydrogen, the thing that it uses and like, takes apart and puts back together in like during nuclear fusion. So if it has like more mass, it's going to be like more pressurized in the center of the star, and nuclear fusion is going to happen faster. So anyways, also planets, any planets a star might have are determined by the gas that's orbiting it and ends up forming into planets the minute the star is formed from a protostar. So this whole process takes a long time. So it takes anywhere from 1 million stars for bigger stars, because like I said, they like have more energy and burn through things faster. This is just like the forming of the star though. So this takes anywhere from 1 million to 10 million years. So yeah, the actual lifetime, like the whole lifetime of a star, it depends on its size. So, like I said a second ago, I'll say it again. Stars with more mass exert more gravitational force on their core and also like on their whole thing, but specifically in their core, which means that there is higher pressure in the core and thus speeds up the process of nuclear fusion. And it also means that the stars burn through the hydrogen that they have more quickly, and so um, the term for it, they die more quickly. Um, it's a term. Anyways, stars last anywhere from a few million to hundreds of billions of years. So also star clusters are a thing. They tend to form from the same kind of like cloud of gas or nebula. And because they're forming from the same like gas cloud, they are the same age, but they're not necessarily the same size. So globular clusters are typically older and larger, and they're bound by gravity. So globular, I guess, it just means it's a glob. um, so I don't know. Yeah, it's just like a spherical like cluster of stars that's like centered around a specific like glob of stars, and they're bound by gravity. Open clusters are still formed from the same like kind of gas cloud, but they aren't bound by gravity, unlike globular globular clusters. Okay, wait, I'm just gonna check the waiting room one more time to see if I have anybody. Okay, no. Anyways, that's okay. Um,
Where's Sage Official?
what did you say?
Where's Sage Official?
I don't know actually. Um, they told me that to just, record the meeting and it would be okay. Is that okay with you?
Yeah, but like I've never been in like a class with only the teacher and me.
I know, it's a little weird. I think this is just a weird time. But uh yeah, I'm recording it and your other students who were here earlier can like still see the meeting if they want to.
Also,
I
I
don't know.
searched up globular star cluster and I found the exact picture that you put on in the slides.
I know. I might have gotten it from there. I'm glad you're looking things up. And by the way, do you have any questions? Because do you have any questions?
Not really, because like usually, like if I join late, I just try to figure out what's going on.
Good. That's really good. You're really smart. Okay, I'm glad you're keeping up with everything. Anyways, um, but if you do have questions because it's just us, I guess, just say anything. I'll answer it. Okay. Okay. You probably heard me. Thank you for staying. I'm glad you're here. Anyways, okay. We're going on to the function of stars. Uh, okay. So this one is a little bit of a hard concept, but basically, when stars are born, they can be composed of a bunch of different elements, but specifically, they're mostly composed of hydrogen. This is because, like, during the Big Bang, hydrogen and helium were two elements that were created, and the rest of the elements have all like been created by stars by nuclear fusion. But original stars only really have nuclear uh, whoa, original stars only really have hydrogen and helium inside of them. So, yeah, basically what I said, supernova are typically made of lighter elements, hydrogen and helium. If you look on the periodic table, it kind of makes sense. They only have like a proton and a neutron in their nucleus. I don't know chemistry, but yeah, anyways, the stars are very massive. Like, no matter what type of star you're talking about, it's really big. There are certainly stars that are a lot bigger, but the stars, if they are undergoing nuclear fusion, they're really big. So this creates a lot of pressure and temperature at the center of a star. I said this a minute ago, but this means that matter is in the form of plasma. So that means that electrons have gone off the nucleus and the nucleus gets taken apart and these parts get like squished together, um, or like when atoms are put under a lot of pressure and squished together, they break off into building blocks, nuclei, and then because they're all squished together, these broken apart nuclei end up gluing themselves back together. And they form larger atoms like helium and also carbon, nitrogen, basically every other different atom, up to iron. I'll talk about that in a second. But basically, nuclear fusion is when lighter elements like hydrogen are put under a lot of pressure. They break apart and get put back together into different elements. Something specific to like understand is that no matter is actually being like created. It's just things being like taken apart and put back together. This produces a lot of energy though. As you can see from this thingy, you have two different, where is my clicker? Okay, you have two different like kinds of elements that get put together into a new thing, and it creates certain particles and also a lot of energy. This is a more complicated diagram. I
To get,
think this is really interesting. Oh wait, what did you say?
to get onto the laser, you can also just press the L button, like on the keyboard.
Whoa, you're right. That's really cool. Okay, I didn't know that. Thank you very much. Okay, I know. Sorry, I always like be like, where is my laser? Okay, anyways. Um, this is a little bit more complicated diagram of nuclear fusion. But anyways, this creates new elements. It also provides the light and energy that we get from the sun and that we see, the light that we see from a bunch of stars all throughout the universe. So nuclear fusion has multiple products. Of course, it has the new elements, like I said, carbon, nitrogen, helium, all that. It also has photons, which are light, and other subatomic particles that I'm not really going to get into, but if you want to look at that up, you can. Anyways, stars, if they have a solar system, they serve as the they serve as the center of their solar system. And for us, they serve as, they help like us navigate throughout the sea. I talked about that on the first day. And potentially, if we want to do space exploration, they would help us navigate the galaxy, which is cool. Anyways, onto like the composition specifically. So, oh no, I don't have a lot of time. Okay, I'm gonna try and get through this, but okay, so the age and size of a star determines its composition. So the older a star is, the longer it's had to do nuclear fusion. So this means that it has like more diverse and more heavier, and heavier elements inside of its core. So it has different elements that it can do fusion with. So the as it like goes on with its like fusion process, it produces helium and then carbon, and then it starts doing oxygen, neon, keeps going on. So the older a star is, the heavier the elements inside of its core are going to be because it's had more time to like produce them. But also stars can't produce elements that like it doesn't have enough hydrogen to produce. So like if a star is smaller, it might not get to the carbon fusion phase because it doesn't have enough mass to sustain that continuous hydrogen fusion. It'll just like run out of fuel and it'll stop fusing and it'll reach its end state, which I'll talk about in a minute. But larger stars create much heavier elements like iron. So yeah, I'll. Oh,
I think it could like when stars die, like they explode kind of, and then I think like I forgot.
oh my gosh, yes, I'm going to talk about that. They explode into things like supernova and planetary nebulae, and they also form black holes. You are very right. Thank you. Okay. Um, anyways, so this might be a little bit boring, but uh, yeah, if a star is more massive, it can produce a bigger like variety of elements. Uh, yes. Anyways, so nuclear fusion occurs because of the pressure and temperature that atoms are put under. But once you get to a certain point on the periodic table, it actually takes more energy to like start nuclear fusion than you actually get out of it. I'm not sure chemically why that is, but basically iron, once you get hit that point, stars actually don't have enough pressure to put to make like atoms before iron break apart, or no, wait, to specifically make iron atoms break apart and start fusing with other iron atoms. So this means that the like heaviest atom that you can produce in the center of a star is iron. So yeah, basically when atoms are large enough, more energy is like needed to be put into fusion than is actually given out by the fusion. And this isn't sustainable for the star. So the star will start to collapse because there isn't fusion going on in its core anymore. And it isn't exerting that outward pressure that I was talking about a few minutes ago, that like allows it to be in equilibrium and not collapse. So it has no more energy going out, so it's just going to collapse. Um, Okay, so types of stars. So I said this a minute ago, but like the most important part of a star is its mass. Um, and this mass ends up like determining its size because of like the equilibrium that it reaches. Stars are also classified by their temperature. So hotter stars are blue and cooler stars are red, which is a little weird, but temperature is really important, and also by their luminosity. So cooler stars are going to be like give out less light, and brighter stars give out, or hotter stars give out a lot more light. So there are a bunch of different classifications that you can give a star. I actually don't know that much about this, but as you can see, kind of hotter stars are, I guess, called O stars, cooler stars are called M stars. This is some really like technical stuff, but if you really want to look it up, you can. But basically, what you need to know is that scientists can look at a star's temperature and brightness, and they can determine like the distance. So if they know the color, they know like what stage of life the star is in, and therefore like how much brightness it should be giving out. So if they know how much brightness it should be giving out from the measured brightness they see when they look at it in the sky, they can figure out that it's this like however far away, because it's like dimmer than it would be if it was like close to us. um, they can also determine the age of a star if they look at its size and temperature. They can look at the typical like life cycle that a star goes through and figure out how old the star is. So from like protostar, a star like undergoes fusion for a really long time, and then it gets to a point where it can't fuse anymore, and then it might expand, but then it might continue fusing with like the other elements that are in the star. It's a little confusing, but the star goes through a bunch of like expansions and compressions, and eventually it can't fuse anymore, because of it doesn't have enough pressure, it doesn't have any like elements other than iron, all of that, and it'll stop it. It will explode. So there's something called a Hertzsprung-Russell diagram. I have a little picture of it over here, but basically it relates the star's surface temperature. So we measure that through its color, um, with its like intrinsic brightness. Um, and they place it on the diagram. And as you can see, there's kind of a little pattern here. This is called the main sequence. So normally stars will like travel through this sequence, or they will just like be on the sequence and travel in patterns like around it throughout their lives. Um, I don't really know how to explain that. But yeah, it's a plot of the star's temperature versus its true luminosity. This one is like it shows the size specifically. So these are like cooler and like um, less bright stars, and they're also smaller. And these are really hot and really big and really bright stars up here. And these are really bright stars, but they're also cooler, which is a little interesting. We'll talk about that in a minute. But um,
I searched it up and like there's like neutron stars, white stars, red giants,
yes,
binary stars, supergiants, the dwarves, and like a lot
look,
more.
yes, look, I have a bunch of these. Okay, I'm glad you're really interested. Okay, so I'm going to talk about equilibrium, and then I'll get on to the end states, I promise. So Uh, yeah, anyways, nuclear fusion requires pressure to occur, but it also exerts an outward pressure. And once fusion isn't going on anymore, the star will start to collapse. And once it runs out of hydrogen in its core, it will begin to collapse because the star, like, no more fusion is happening. And then the star will explode because the all the mass like collapses inward really quickly, but then it like hits the core, which is solid, and it bounces outward, and that's what causes the explosion. So like matter is around the star, or like the outer layers of the star collapse inward, they hit each other and they bounce outward, and this is what caused this explosion. So this is like specifically the outer shell that is exploding into these really pretty colors. So bigger stars, stars that have more energy and more matter, are going to have way more dramatic ends than smaller stars because they have more like um, gravitational energy. And so when the stars like collapse into themselves, it's going to be with a lot more energy, and they're going to explode a lot like bigger and brighter and look really cool. So we'll start off with the boring stuff. So very small stars, stars that have less than 0.75 times the mass of the sun. So that's like a very small fraction of the mass of the sun. They aren't.
I think that one's a brown dwarf.
It is. Wow. Okay.
It's like it's the exact same picture.
It is. I got a lot of my pictures from the internet. But yes, this one's a brown dwarf. Um, so basically, what that means is that the star doesn't have enough gravitational energy and it doesn't have enough hydrogen and mass to sustain nuclear fusion. So these stars can't sustain fusion for like as long. So they're really tiny, and they eventually like they don't even explode or anything because they don't have enough energy. They just kind of like cool off, and they live the rest of their lives as like cool. I don't know why I said gas clouds, just as like cool clumps, like as in cold clumps of gas that it's just like swirling around. This one's a bit of a boring end state, but red dwarfs. I don't have a red picture here, but stars that are between 0.8, so that's just a little bit bigger than brown dwarfs, and 0.4 times the mass of the sun. It's still smaller than the sun, but they undergo fusion for a very long time, but they eventually run out of fuel, of course, and they collapse. But because they're not big enough, they don't like explode or anything. They just, oh, my cat is here. They turn into things called white dwarfs, which you can see here. You can see it's kind of the size of the moon-ish. And it's a cloud of gas that is glowing white because it has like, it's really hot, but it isn't actually doing fusion. It's just kind of sitting there. And it cools down over the course of its life. So it's just sitting as a white dwarf, which is a little bit boring, but basically it's not big enough to do any sort of explosion, but it's a little bit bigger than a brown dwarf, so it's going to look a little bit brighter.
I have a
Um,
cat, and her butt looks like your cat's butt.
okay, that's nice. What's your cat's name?
Iris.
Oh, my cat's
Like
name is
if I
Jackie.
just say her name and I clap, then like she knows I'm gonna give her treats, so she just gets up and then runs to the cabinet where the treats are.
That's really cute. Okay. One minute. Let's finish the lecture. I have a few more minutes, but I'm glad you have a cat. So stars that are, I don't know, did I use the same? Oh, okay, yeah. Stars that are bigger than the last group, anywhere from 4.4 to 8 times the mass of our sun. So this is the same sort of category that our sun is in. This is what our sun is going to do when it runs out of energy. But they run out of fuel, different elements, and they expand into red giants. And they kind of live as that for a little bit. I forgot the specifics of what red giant is, but I don't think it's undergoing fusion, but it's like expands outward. Um, but then, did I write that right? Okay, I'm not going to read it. Basically, they explode outwards or expand outwards, but then kind of gravity pulls them inwards, and they do the thing I was talking about earlier. They collapse into themselves, and then they explode. So because they're bigger than the previous like sort of star, they have a little bit more mass. So the center of the star, you can see here, I'm pretty sure that's what that is. It's still going to form a white dwarf in the center of it, actually. It's the same kind of thing as this one. But because it has a little bit extra mass and like different sorts of elements, it's going to explode out into what we call a planetary nebula. So this really pretty thing, okay, I didn't include any more pictures, but um, these kinds of intermediate stars explode into planetary nebula with nebulae with a white dwarf at their center. And these planetary nebulae end up like expanding and they end up forming more stars. It's not called a planetary nebulae because it has a planet in it yet. It just, I don't know why it's called that actually. I think like the person who discovered it thought that it was a planet in the sky, but it wasn't. It was a planetary nebula. But yeah, they these kinds of intermediate stars end up um, exploding out their gas, but it's not as violent and dramatic as very large stars. So very large stars don't last as long because they have so much mass and they're exerting so much pressure on their core. So the center of the star burns really, really quickly, and the star will like promptly expand and then collapse when it runs out of fuel. And this collapse makes it explode because it like bounces back and explodes. And this takes like a few seconds just to like explode into a giant cloud of gas. So this is what we call supernova. And depending on how much mass was in the star, it will the supernova will either leave behind a neutron star, which is just a bunch of neutrons packed really, really tightly, and still has like a supernova around it. I don't have a picture here, but it's a bunch of neutrons that are packed really tightly because there's so much gravity that they kind of they like shed their protons and um, that like electric forces don't repel them from each other anymore, so they can like be really compact. Or it can become so compact because it has so much mass put into such a small space that it forms something called a black hole. Um, and black holes, as you might have heard, are pretty cool. They suck in, like, they have so much gravitational force that they suck in, like, everything around them. Um, and even light, so that's why they're called a black hole, because you can't even see anything coming out of them. There's because they are their gravity is so strong that they suck in light. So I'm going to talk a lot more about like galaxies, supernovas, black holes next week. I just wanted to provide a little bit of introduction and explanation that these kinds of things, black holes and neutron stars, are the result of very large stars not undergoing fusion anymore, reaching their end state, exploding. Um, okay, so over here we just have a summary of like what has been the entire lesson today. So we start out with a nebula, and this gas is just kind of floating around everywhere and doing its thing, and then it starts to like clump in this big dust cloud, and these clumps end up apparently forming something called a globule. I didn't know that, but this is basically just like the more dense clumps. Eventually, those clumps get so dense and have so much gravity and so much mass, they end up forming something called a protostar with a protoplanetary disk of gas orbiting around it. And either this star didn't really gain enough mass to become an actual star and it becomes a brown dwarf and just kind of sits there, or it has enough mass and it becomes something called a main sequence star. I didn't get too much into that, but it basically just means it's a star that you can easily predict its like life cycle. And then it might expand and become a red giant, and then it condenses down into a white dwarf or a black dwarf. I should know what black dwarf is. I think it just doesn't have a lot of energy, or supernova, or neutron star, or a black hole, depending on its mass. So this is something that explains a lot better, like the mass. So something that's really small is just going to kind of sit around and become a brown dwarf. It's not really going to do anything, a red dwarf, or it's going to be something that's the size of our sun roughly and become a giant star, and then even giant, maybe like an even bigger star, and then a planetary nebula. It's going to like expand and become nebula and then leave behind a white dwarf. Or it's going to do like the same thing with the expanding. It's going to become a supernova and then leave behind a neutron star. And then a very, very, very big star is going to get really big, whoa, and then become a supernova. And this one would leave behind a black hole. This one also represents how, like, as you can see, like the size of something determines its temperature. And as things are like hotter, they become like bluer, as opposed to being red and then blue. Yeah, this one is a little bit like simpler. Sorry, it's kind of bad quality, but nebula, the size determines its fate. So yeah, you should, if you want to know more, you should definitely look things up because I might not have done a great job of explaining it. Um, anyways, I have a Kahoot if you want to do it, to the one person who's here. But I guess I'll just like say for the Zoom, I have a little bit of a homework demonstration that if you guys want to watch it, or want to play it, you can play it. Thank you for watching. Um, Zinming, do you want to do the Kahoot? Uh,
Okay. Like, how do you
okay.
choose one person?
Oh, that's a good point, actually. Um, I can just show you the questions, I guess. Am I still sharing the screen?
Even though
Or
I'm
should I play?
already on